The name of my work is Toward Explainable Fashion Recommendation. My name is Pongse Tangsing. This work was done while I was a PhD student at Tohoku University, Japan, under the supervision of Professor Takayuki Okatane. My works tell you how your outfit is bad or not, and point out exactly what to improve. Starting from imperfect outfit, we want to identify the flaw so that the user knows what to improve. We approach this scenario with an outfit grader that is trained using explainable fashion features. Then we use gradient-based class activation map to point out the feature that is the flaw. The contribution in this paper is our outfit feature level flaw detector. My scoring model is trained on 200,000 outfits from now defunct fashion-based social media platform called Polywall, which has likes, comments, and list of items. I use outfits with likes as positive samples and randomly created outfits as negative samples. Each item is separated into main colors and shape and texture. 3 dominant colors from each image are extracted by finding clusters of pixels in the color space. For non-color information, we first convert the image into grayscale, then extract edges, which are expected to maintain the shape and texture of the item. The non-color information edge image is forward propagated through a pre-trained CNN. Then, the output and the main colors are forward propagated through a series of concatenation and fully connected layers, with ReLU to obtain the score. The system also computes the gradient of the score with respect to the representation of each item through backpropagation. The gradients are multiplied with the corresponding features, yielding Item Feature Influence Value, or IFIV. Extracting explainable feature like this loses some information. To see the quantitative effect, we train 2 identical models, one with explainable features, another with traditional RGB images. This table shows that we lost around 3% on accuracy and average F1 score. Since the feature level flaw detection is a novel problem, we need to create our own evaluation method. We decide not to use human-based evaluation method because it is not repeatable. Here, we design the evaluation method as follows. Start from perfect outfits with a very high score from our outfit grader. We call this outfit a base sample. Then, we replace one of the item features, such as edge image wise or color wise, or the entire item as item wise, until the score is very low. Now, that outfit has a flaw. We then use our approach to detect the flaw. If the flaw is correctly detected, the detection is considered successful. By using this method, we start from 1,000 high-quality outfits from Polywall 409K dataset. 54,770 flawed outfits are created. This is the distribution of outfit score of each type of sample. Since we use high-quality outfits as base samples, their scores are very high. For item-wise, color-wise, and age-wise sample, the scores are distributed as shown in the figure. Now, let's talk about how do we evaluate. Now, let's see some examples. From this base sample, as you can see that the outfit is very good, and the IFIV values are almost zero or minus. It shows that this outfit doesn't have any flaw. But for the item Y samples that we created from this outfit, we replace the last accessory with a bag, and we can see that the item Y's IFIV is very high, also with the edge image IFIV, but not the colors. This value shows that by replacing this item, the color is not so bad, but the edge image and the overall items is very bad, and is the flaw in this outfit. And obviously, our model can detect the flaw correctly. In this example, we show that we replace only the edge image, and the IFIV show that the edge image on the feed part is very high, higher than the item, higher than the color. It means that in this outfit, the shape and the texture is not matched with the entire outfit, but not the colors. For the lower samples, as you can see, the color doesn't match at all, but the shape of this accessory, which is the necklace, is okay. Our model can also detect this flaw, as you can see from the IFIV, that the color IFIV of that item is very high. It means that our model can detect the flaw correctly. This is another example, which is totally different style from the previous samples. But in these samples, we replace the necklace with another bag. And as you can see, the style of the bag doesn't match with the entire outfit at all. And our IFIV value can identify that perfectly. In this example, we replace the shoe. And as you can see again, our IFIV value identify that the flaw of this outfit is on the shape and the texture of the shoes. On the last samples, we replace only the colors, and again, our IFIV values can identify that colors very well. This table shows the overall accuracy of the flaw detection. You can see that our proposed method can detect item Y flawed 99% of the time, as well as the edge image Y is flawed at 99% of the time as well. For the color Y, we can detect the flaw at 81%. This table shows the accuracy of our flaw detection on different outfit parts and different flaw types. The overall accuracy is very high. On the item and edge image is almost 100% all the time, but on the colors, it is around 50%, 60%, and 90%. It can go as high as 94% as well. But in comparison, by chance, it's only around 9 to 10%. As a result, our method can detect the flaw effectively. Thank you very much for your attention.